Welcome everybody. It is a real pleasure to welcome Cephise Cacho today. He is the principal beamline scientist of the IO5 beamline at diamond source. IO5 is the beamline that is dedicated to ARPES spectroscopy, and Cephise will tell us all about it today, talking about the fundamentals and what it can be applied to. So before joining Diamond, Cephise was a senior researcher at the Central Laser Facility. He in Central Laser Facility here at Harwell. He was, well, his area expertise was time resolved ARPES spectroscopy with ultra-fast laser sources. And before that, he was at Electra performing time and spin resolved photoemission. So he had quite a lot of experience in ARPES, and I'm sure the seminar will be really interesting and enjoyable. So, Cephise, without anything else to say, when you are ready.
Thank you, Sophia, for this nice introduction. Let me just share my screen. I don't know if you can share. You should be able to see it. That's right.
It's doing it. Yeah. It's not in presentation mode, but it's. And
now, yeah.
Now it's perfect.
Okay, thank you very much. So, good afternoon, everyone. And this afternoon, I'm going to talk about ARPES. And the question is, what can we learn from the ARPES technique? Obviously, there's a lot. And in 45 minutes, it will be difficult to explain everything. And I didn't want to give you too many examples on very nice results. So I thought we can just go through how we do the measurement, how we do the process, how we analyze the data, and then give you some quite interesting results that I've selected. I won't talk about spin ARPES or time resolved ARPES. This is could be another presentation. But also this talk is geared toward scientists who doesn't have much experience in ARPES, so it's also to learners. So the outline of the presentation, as I say, we're going to talk about the instrumentation, so the photon source and how you do the measurement with the high resolution ARPES and nano-ARPES, and how we do the measurement, the sample preparation. So this is just to put in a context to see what it is really in a real life. And then we can spend a bit of time here to look at what kind of information we can extract and how we process the data, how we analyze the data. And then there will be a few examples of nice results about superconductors, fermion, 3D direct fermion, well fermion, and 2D material, tungsten selenite. So the first thing is, what is ARPES? Name stands for angle resolved photoemission spectroscopy, which is a electron out technique. So what we do, we're doing the spectroscopy of the emitted electrons. So in the vacuum, we're measuring the energy and the direction of this electron. Then this is in order to retrieve the original state of the electron in the material before the photoemission process. And so that's the band mapping. And another important thing is, in a strongly correlated system, then you can also see signature of the many-body interactions. And that's very rich physics, which has been really the core of the ARPES over many years. One of the elements we have to be aware is that to be able to do an ARPES measurement, you do need to have a periodicity, a 3D periodicity or 2D periodicity. So it could be just a single atomic layer, but a periodicity is single crystal. And this is to be able to define with this periodicity the block state. And this block state have the electron momentum as a good quantum number. So this is really the main constraint for this. And so what we're going to do here, we're going to talk about high resolution ARPES. So we want to study the states, the low energy states, which are very close to the Fermi level. So this is just the top of the valence band, and also sometime on the conduction band when it is occupied. So how we do this, and this is an example, but this is a beamline, the IO5 beamline, and many beamlines are relatively similar. So we have a photon source, a collimating mirror. We'll come back to those in detail after. The monochromator to select the photon energy with the slit here, and then we focus the beam on the on stations. So there's two on station. There's one for high resolution, so low temperature, high momentum resolution. And then there's another on station with a bit some technical difference, which is for nano-ARPES, so sub-micron ARPES. So the beam here is focused very tightly on the sample. So the source is an undulator. So basically it's an array of magnets which create an oscillating field in which the electron will oscillate and generate the light. This is in a ring. But the particularity of this magnet is that the periodicity has to be quite long because we want to reach the low energy between 20 to 250 eV. This is a low energy beamline on the synchrotron. And so you need to have a long periodicity, 140 millimeters, and many periodicity to get a good flux. So this is a 5 meters long undulator. Then the monochromator, I mean, to explain the system is a plane grating monochromator. So you have a mirror, and then you have a grating, and you adjust the angles of this to select the energy you want to send it to down to the beamline, and then you take an exit slit to select it. Most of the time we work with an 800 line per millimeter. For the spatial resolved, we work about with a 400 line per millimeter. It gives you less resolution, energy resolution, but more flux. And we do measure the energy of the photon after the monochromator. So this is by measuring, for example, here, the ionization in helium. So that's the photon energy that we scan like this, and we look at the ionization here. And you have a final resonance. By fitting this data, we can have extract the broadening, which is about here 3 millieV for a photon energy of 63 millieV. And this means a resolving power of 21,000. And as you go lower in energy, you can do that similar things in neon, and then you can get an energy resolution of less than 500 micro EV for a photon energy of 20 EV. So this is 47,000 resolving power. So this is really the point of an ARPES beamline, is to work with very high resolving power on the photon, and also a detector to match this. So in terms of experiment, this is where we do the experiment. So you have the light coming from the synchrotron, and we will see there's two on station, one for the high resolution, where we push the performance of the ARPES technique to the best resolution, low temperature, and another one on station, which is for the spatial resolve. So this is where we put the beam, we focus the beam very, very small, as small as possible. And we will I'm going to show that, two of them. So the high resolution ARPES is a chamber which is made of, well, it's an on-station made of different chambers. You have the analyzer, which is here, and where you're going to do the measurement. The photon beam will come here. I'll show this in the video after, okay? And then there's a chamber to prepare the sample. We'll see the cleave of the sample, and there's a different chamber to transfer the sample from air to the vacuum system and to store the sample here as well. What is important is to have a manipulator that we can adjust the orientation of the sample as we want, and this one has 6 axes of degree of freedom, and also to be able to go to low temperature. This analyzer is an MBS analyzer. It's a new analyzer we put here. So it looks like this in reality. This is quite compact, in fact. There's a lot going on. So this is where we do the measurement and the upper chamber. So if I show you this video, you will see how this works. So this is the on session, the experimental session. So we're turning around to go to see where the beam comes. This is a beam of the light coming here in the measurement chamber with the analyzer here. I hope you can see the mouse. And then you have a different chamber for preparation. So this is how we prepare the sample. We take a sample plate, we put a copper post, we glue the sample here, the black part here, and we glue a ceramic post. And this is done in air, or some case in glove box. And then we take this element and we put it in the chamber, the load lock, close it, we pump it, and then we transfer it from one chamber to the main manipulator, which is this one here. And when it's on the manipulator, we come with a rubber stick and we break the sample in two to leave a clean surface, because that was a bulk at the beginning. So that's the best preparation we can do. And that's about the different degree of freedom of the manipulator. Then we lower the manipulator, and then we sound the light on it, and the photoelectron goes in the analyzer, and then they are detected at the end of the analyzer, where you have two axes. You have the angle of emission on the bottom, and you have the kinetic energy of the electrons. And it's by rotating the sample, we can have different variation here, and that's how we rebuild the bound structure of the Fermi surface. And there's different way to do this. This is just for demonstration, because in practice we don't use it too much, but it's to show that when you rotate the sample, you can record different bond dispersion, and then you rebuild in 3D here. This is just a sketch, a cartoon, but that's a video with real data. So this is a iron selenite. This is a Fermi surface. So this is in Kx and Ky. This is the intensity, which is took just on this line here, just on this line. And there's area where there's a less intensity. Basically, there's no spectral weight here. And then you can see it here and here. So this is electron pocket, hole pocket, and this is how it is. And you can see here as you turn the sample, the photo emission goes in every direction. It doesn't matter too much the incidence angle of the light for the momentum. For the polarization is a bit different, but this is how it is done. So this is how we do for the high resolution ARPES, where we have a beam about 50 microns for size. Now, if you want to do spatially resolve, you have to focus the beam to a very small size, sub-micron. And for this, we cannot rotate the sample, because otherwise we're going to lose a position. So that the on-station is designed differently. This is where we put the sample, as we've seen before. And this is the goniometer, which is replacing the manipulator. So it doesn't have 6 axes, but 5 axes of freedom, so we can orientate the sample. And then in front of this, we put the optic system to focus the beam. And that's a stone plate. There's 6 degrees of freedom here. We have also a capillary mirror, which are a different technology. And I mean, there's 2 other degrees of freedom. So this is inside, in the center of the experimental chamber. And you can just adjust it for the sample with the analyzer. And also what is very important is that you can rotate the analyzer. So now you can rotate the analyzer, do the same mapping before, but without moving the sample. And that's a major difference between a nano-ARPES chamber and a high resolution ARPES chamber. And you can see this on this picture here. This is a picture of the on-station, of the nano-ARPES on-station.